Alright, so cross sections. Almost done. We have three more problems. Yep, three more problems and then we're done. So this is lengthy. The reason why it's lengthy is because there's a lot involved. There's a lot of breaking the pieces down piece by piece and figuring out what is it that I'm looking for and what do I know from geometry that I can basically alter so that I can find certain lengths that I'm assigning with variables. So it's not too bad. You just need the practice with it. Alright, so let R be the region bounded by the graphs y is equal to 3x and y is equal to x squared. So let me do this again, color coordinated. 3x looks probably something like, whoops, a line with a slope of 3 going through 0, 0. And then x squared we'll do in blue. Y is equal to x squared. And draw a figure and shade the region, or the bounded region. Okay, so then find the area of R. So all we did was we drew the two. Here's the area of R. This is the shaded region, bounded. Okay, bounded because you have a top, you have a bottom, and then you have closed intervals. It doesn't just open up like this one. This is non-bounded because it would just grow forever. It doesn't have another endpoint where they meet over here, bounding it. Okay, so this is the bounded area. We're going to call it R, and we're going to find the area R. So this is just a little bit of review. So looking at this, we're going to say from this low to this high, AB, I can do that by looking at the intersection, and I'm going to show you right now with the calculator. 3x, menu 3, 1, solve feature. When does 3x equal x squared? Okay, and then you're going to do comma x and close, because we want to know when do these two functions equal each other. And it will tell us with the solve features. We just have to do control enter, and we get 0 or 3, which makes sense because if I put 0 into this function, I'll get 0. Here I get 0. Okay? So 0 yields 0. They're the same there. Okay? That's where their y values are the same. And then the other one was 3. And that makes sense because if I put 3 in here, I get 9. If I put 3 in here, I get 9. So then there again, they're going to be the same. That goes without saying. Okay? So 0 to 3, and it'll be top minus bottom. The top is 3x minus x squared. And technically, yes, I know that this is in parentheses and this is in parentheses. But because the fact x squared is a monomial, you really don't need it. You could just write it just like that. Okay? And this is the area of the bounded region. So we would say 3x minus x squared. So let me go ahead and make it a definite integral. It's from 0 to 3. And it'll be 3x minus x squared. And then it's going to be in respect to x because they were vertical slices. And my answer is going to be 4.5. Or if you wanted to have it as a fraction, 9 halves. Okay? So it's equal to 9 halves units squared because we're looking for area, not volume. Okay, so here are those vertical slices. This is a review-ish type of problem, but that's what you would get. Chances are, well, most likely you would do this by hand. I would need you to show this work. I would need you to show 3x squared over 2 minus x cubed over 3. From 0 to 3, I need you to show this work that I just did. And then at the very end, you would show everything going into play, like 27 over 2 minus 27 over 3. So we could say 9. And that's minus 0 over, or minus 0, because the rest of it is 0. So you have 9. Let's make a common denominator. You have 18, so 27 minus 18. That's where you get that 9 halves. Alright, so the same thing. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an equilateral triangle. So it's the same picture, only they're equilateral triangles. So that this is the base, it would pop up. This is the base, it would pop up out of the paper. And try to picture, again, that three-dimensional rendering of what it would look like whenever it does do that. And if you need to refer to the Wolfram demonstrations, by all means do so. Okay? So it's popping up out of the paper. And we're using that same thing. These are fun because we just have to set them up. We don't have to actually do them. But we have to make sure that when they're this easy-ish, and I say easy with quotations, you just have to make sure you don't mess up on any of the accountabilities of bounds or the integrand itself or what you're in respect to. So here we go. Perpendicular to the x-axis. So again, if you need to, here's the x-axis perpendicular. That was a vertical slice. So you know it's dx. Okay? Equilateral triangle. Because you're trying to find the volume. So you're going to do, like this, equilateral triangles. Okay, so that goes back to this shape over here that I was looking at. The equilateral triangle is the base, that length that exists in between. So let me highlight that in green. That's what I've been doing a lot. That base will be the length between the two functions, which is top minus bottom. So 3x minus x squared, that's the length of that green base right there. And it's changing throughout. Okay? So the base is, first of all, let me do the, I need to find a of x. And I will integrate, as I saw over here, from 0 to 3. So we just need to come up with an area formula for this equilateral triangle in terms of x. So we know equilateral triangle side squared root 3 over 4. Okay? And we need to come up with the length of the side. So that length of the side was over here as far as that entire green line that I just drew right there. We need to come up with that because that entire green line represents the length of the side of each and every one of those changing equilateral triangles. So top minus the bottom. Going back, our top was 3x minus x squared. This is the length of s. So s squared, the root 3 over 4, you can constant multiple roll that thing out. It's still dx, and it's going to be from 0 to 3. There's my answer. I don't even have to evaluate. It said set up, but do not evaluate. Okay? That gives you the volume of the solid. So this you could say, and if you wanted to, you could say units cubed if you want. But it's not necessary. It's just saying what is the expression going to be. Okay? So now let's go to the very last part. Set up but do not evaluate. Instead of an equilateral triangle, we're going to have squares. So again, real quick, I'll just draw the picture. You have this, then you have the 3x. Okay, and it's still perpendicular to the, hold on a bit. Perpendicular to the x, perpendicular to, okay, so perpendicular to the x, this is different. Perpendicular to the y-axis. I'm glad to slow down a little bit. So perpendicular to the y-axis, they're not going to be vertical slices. dy, they're going to be horizontal slices. Horizontal slices. So they look like this, which makes sense because the red's always on top of the blue. Okay? But I mean, either one on this example obviously work. Both of them, vertical and horizontal, because one's always on top of the other depending upon what orientation I'm looking at. All right. So dy, I need to solve my functions for x, because I'm trying to get x in terms of y. So my function was x squared and 3x. So solving for x, I get x is equal to plus or minus square root of y. Technically, I'm only going to interpret this as the positive square root of y. So let me erase this negative one. It's not accounted for because this negative one, it's this one over here, but I'm not even working anywhere near that bounded region. Okay, so x is equal to root y. And the other one is x is equal to y over 3. So y is equal to 3x. X is equal to y over 3. Now I have those functions, equivalencies, written in terms of y. So I need area in respect to y, because I'm integrating in, area in terms of y, because I'm integrating in respect to y. And I'm still going to go from 0 to 3. Hold on, let me make sure on that. Let me come back a little bit. So this was 0, and this is 3. It's not 0 to 3. It will be from 0, 0 to 3, 9. So when I did vertical slices, okay, on that one right there, I went from 0 to 3. Because I'm looking at from the x to x. But when I do horizontal slices, which is what you see here, it's going to be from the low y to the high y. So it's not going to be 0 to 3. This is, again, these are those small little minute mistakes people make. That's why it's just a set up but do not evaluate. So it'll be 0 to 9, low y to high y, dy, because I'm in respect to y. And now I just need to do the top function. Okay, let me highlight that in more green. So the top function minus the bottom function. And the bottom function would be right here. And again, that I'd have to tilt my head. I don't have to tilt my head yet again for the bounds, but I do have to interpret top over bottom. So the top function is right there, root y. Not x squared, because I have to write it in terms of y. Okay? Minus the bottom function. The bottom function would be y over 3. So top minus the bottom, I wrote them both in terms of y, again by solving for x, and we did that before. And it's in respect to y, it's from 0 to 9, and if you find a mistake, by all means let me know. If this looks pretty good, that looks like that's my answer. And if you want to put units cubed, you're more than welcome to, because of the fact that you're doing volume. But I'm looking for the expression. You really don't have to put units cubed, only if you have a quantitative amount. That's when I'm really going to be a stickler as far as your units cubed. And that's it. That's all that we are looking at right now. I was going to do the washer and disk method, but I'm not going to include that in this video. I'll include that into the next one after all.